Okay, so let's look at Nesterov accelerated gradient descent. So now we know that momentum-based gradient descent is good at these gentle regions. It moves really fast, but we still don't like it because it has this problem of oscillations. It has this problem that it overshoots its objective, right? Its goal, and then it has to take a lot of U-turns. So can we do something about reducing these oscillation? So the answer is always yes. So let's look at Nesterov accelerated gradient descent. Okay. So the idea here is very simple. Look before you leap. Okay. Now remember that this was the update rule for momentum based gradient descent. Okay, and I'll write it down again. Wt plus 1 is equal to Wt minus gamma into update t minus 1 minus eta into the gradient at the current point. Okay. So you see that actually I am taking two steps. One is this step and then one more step. Right? I could just, this is one way of visualizing it, right? That I move according to the history and then I move a bit more according to the current gradient. So everyone sees that there's a two-step movement happening here. Okay. Now can you think what could have been done? Look before you leap. Okay, so we'll see what we can do. So we know that we are going to move at least by this one, right? That's fixed. We know that our history is telling us to move at least by this one, and then we'll move a bit more by the gradient. Okay. So now can you think about it? I'm at least going to move this much. What if I had some way of looking ahead and then do something at that point? Is this what you're saying? Of course I can verify it, but I am sure it will become clear once I show the equations, but I just want you to think about it a bit more, right? It's very simple. It will become absolutely clear once I show you the answer, but just think about it a bit. Okay, so here's the answer, right? Why not compute the gradients at this look ahead point, right? So you are again adding it in two steps, minus the history and then minus the current gradient. So take this value, call it the look ahead point. I know that I'm going to move by this much. So let me not compute the gradients at the current point. Let me move by this much, then compute the gradients and see what happens at that point. Does it make sense? Okay, so this is the equation, right? That first I move by that one step. I had to make a two-step movement. So I'll move by that one step, right? Then I'll compute the gradient at that position, not at my current position, right? This was earlier gradient at point T. Now I have already moved a bit, so I can compute the gradient there and then move in the direction of that gradient. Does that make sense? How many of you are completely lost? You are completely lost? Okay, good. I mean, not good, but yeah, good that you raised your hand. Okay. So, okay. So you understood this, that there's a two-step movement, right? Wt minus history minus the current gradient. Gradient computed at time step t. Okay. Now you know that you're already going to move by the history, right? So why not just move there? And then compute the gradient at that point. So you're anyways made some movement. You compute the gradient at that point and then decide which is the direction to move in, right? So that's what this look ahead value is. Okay. I know it's still not clear to many of you, and I'm very confident it will become clear in the next 5 minutes because I'll show you one more visualization for this. But just stay with me for a while. As long as you get the intuition, I'm fine. I'll move ahead and then I'll explain it again in a different way. Okay. Is this fine? That should become clear. Good that you asked that question. Okay. So ask me again on the blank slide that I have, and then it should become clear. Okay. So for right now, let me just show you what will happen with the code, and then I'll again explain it with a different way. Okay. Okay. So this is what momentum-based gradient descent did. Okay. Now let's see what Nesterov accelerated gradient descent will do. Again, the code is simple. You can just read it up. And now I've started executing. You see this blue curve coming over there. Fine. Okay. And now I keep running this. Now what will happen? You see that all the U-turns of the blue curve are inside the U-turns of the red curve. So the objective is being achieved, at least empirically I've showed you that, right? It's taking shorter U-turns. What is probably not clear to all of you is why is this happening? Is it clear to everyone why is this happening? Can everyone visualize that? Okay. So let's see why this is happening. I'll give you an alternate explanation for this, okay? So, okay. So suppose this is my error surface. I drawn it too big. And I have a single variable with respect to which I'm trying to optimize. So this is my W, okay? I started off with some initial value W0, okay? Now, what is the gradient at this point? Positive, negative? Negative, right? Because when I'm going to increase W, the function is actually going to decrease, right? So, the slope is negative. So, where will I move? This is the number line, right? So this line is actually the number line because it's a single variable. So where will I move? Positive side of the number line or the negative side of the number line? Positive side. The derivative is negative. I'm going to move in the direction opposite to the derivative. So I'm going to move in the positive direction, right? So I'll end up somewhere here. Is that clear? Fine with everyone? Okay. So now I am somewhere here. What's the derivative at this point? Okay. Now what's the derivative here? Positive, negative? Negative, right? When I'm increasing W, my loss function is decreasing. So my dl by dw is going to be negative. This is positive, this is negative, right? Okay. So again, I'll move in this direction. So what is happening? A lot of negative updates are getting, a lot of positive updates are getting accumulated, right? And now because of my momentum, I am not going to move only by this derivative, I am also going to move by the history, right? So I'll end up somewhere farther. Okay, is that fine? So now at this point, what is the derivative? Again negative. When I'm increasing W, the function is decreasing. So what is my update? Positive or negative? Positive. So now you see that a lot of positive updates are getting accumulated, right? My momentum is building up. So now what will happen? Now if I just move further, then again I'll get a, let me just put it here, right? So I'm again moving largely in the positive direction because this guy is also positive. All my history was also positive. So I moved in the positive direction. Now what will happen at this point? What's the derivative here? No, it's still, it's negative, sorry. So again I'm going to move in the positive side of the number line, okay? Now at this point, I want to break down the movement into 2 points. One is what my history was telling me, which was all these positive updates. But of course, I'll not make such a large update because I'm weighting them exponentially, right? So, but it's telling me to move in the positive direction, okay? And I know that the gradient at this point is negative, but I want you to ignore that for now. I just want you to focus on the history. If I just move according to the history, where will I end up? I'll end up somewhere here, right? Because the history is very positive. So I'll keep moving in the positive direction. And this is my W look ahead. Okay. Now, what will happen if I compute the gradient here? The gradient is positive. So where will I move? Negative. So you see now why momentum works? Because you are able to look ahead to this point. Instead of, what should I have actually done is, I should have looked at the gradient at this point. The history is positive. The gradient is also telling me to move positive. So I would have moved a large positive and I would have ended somewhere here. Instead, I just moved by the history. I checked where I end up. I end up here. Now let me see what's the gradient at this point. Have I already overshot my objective? When will I overshot my objective? If the sign of the gradient changes, right? It became from negative to positive. And now since it's positive, because as I'm increasing W, the loss is also increasing. So now where will I move? Negative. So now what's the second step actually? It's again bringing me close to here. So instead of taking this large U-turn, I end up taking this small U-turn. Is this clear to everyone now? How many of you still don't get it? How many of you get it now? Good. Sure? Okay. So this is what, and now you can relate it to what was happening on the figure. So let's go back, right? So you saw that I was making these smaller U-turns because when I was at this point, right, I already moved by the history. I knew I would end up somewhere here where I would need to go back, right? So I already accounted for that and made a very small movement. Is this clear? Everyone gets this? How Nesterov accelerated gradient descent works? Sure? Raise your hands. So looking ahead helps NAG in correcting its course quicker than momentum-based gradient descent, right? So it's already looking ahead, where do I land up, and already making a correction if required. If not required, it will again move in the right direction, right? So the update is this guy plus the gradient, and my update happens on the original value, not on the look ahead value. So her confusion was perhaps that I am doing W look ahead minus update, where this update again has this quantity, right? That's what your confusion was. But I'm not doing W look ahead, I'm using WT there. Everyone gets this? Okay. So that's where now it's clear that why the oscillations are smaller in the case of NAG, and it's able to correct its course quicker. Okay. So that's where we'll end this module.